Okay, then we can officially start the morning section of today. The first speaker, the first lecture is by Professor VI Silvestrov, Sweden.
Okay. Thank you very much for inviting me here. It's a very interesting conference and interesting topics covered, and even though I'm a mathematician, I enjoy also many other ideas which are coming from other subjects, and also it's quite exotic for me as a mathematician from the university to give a lecture on the stage of the theater and look at the audience down instead of being in front of the blackboard and looking at the audience up. So if I look in the wrong direction, please forgive my my inexperience of staying on the stage of the theater. So it's you see, it's what I will talk about is the some mathematical parts of what Professor Santilli have done in his work, and it's quite amazing that he is able to do both experimental and serious theoretical research, and that's and so I'm a mathematician. Will try to say a little bit more about mathematics, and I will not go into too much details, of course, because that would be out of the conference context if I would go to too much mathematics details. So, but let's try. So there are several motivating points which bring us to these structures, mathematical structures, which Professor Santilli have developed and many other colleagues. And one of the motivation comes from an interesting idea of trying to reinspect special relativity due to some experiments showing that light or maybe some other phenomena in a complex medium behave in a different way than if it is in the vacuum. So that's and there are a series of works by Professor Santilli and many of you working with this which show that basically what is written here, this is what I said. Yes. So if you look at propagation of say light or some other phenomena in a complex medium inside some stars or something, then there are some new things to be developed for me from mathematical point of view. So and then well, it is so that most of the classical formulas and classical results in special relativity, they are developed with certain assumptions, and it is not clear whether these assumptions are coming from really physical side, or they are coming from previous generations of theoreticians or mathematicians or physicists not able to provide mathematical grounds in solving more complicated equations, and so here it's important point for mathematician. It's actually it's very pleasant point that when this happens, that because this means that there are more interesting mathematical problems to be solved, and you can see that one has to develop and more more sophisticated versions of Minkowskian geometry, Lorentz Poincare symmetry, special relativity, which would be valid for this more complicated media, complicated media and conditions where previous physical models maybe are not completely applicable. And one of the points is that one would like to be able to treat varying speeds of light depending on some local parameters, and so sometimes one writes this in this way, where this n is the index of refraction depending on the coordinates and derivatives and so on and so on. And when one has made this extension of conventional assumptions about constant speed of light, then suddenly the all equations which we used to when we look at special relativity not anymore as simple as they have been, and all these questions about symmetry become highly non-trivial, and about metric and so on, because many of these quantities become dependent on all these parameters and coordinates. Okay? That's and again, for me as a mathematician, this is a very pleasant situation. So actually, when I have been studying some basics of special relativity, I have always been wondering, is it really possible to prove mathematically the speed of light is constant, and what are grounds for what are really grounds for this? And actually, it's not really clear. Either you make it as an assumption or you prove it, and if you find and it's for a mathematician situation there is not completely clear. But if one has this assumption that there are physical situations where you have to have variable speed of light, then suddenly new possibilities and new questions appear mathematically, and that situation becomes more pleasant for mathematics. Okay, so there are certain also Professor Santilli developed also something called the no reduction theorems, which basically says that you cannot really resolve this problem, that if you treat this propagation of light in this very difficult situations which are not really subject to previous conditions described by previous theories, then then it's very difficult to reduce it to situations where you really can use the previous theories, and so this. And actually, in 1960s, in his PhD thesis, and then in several very interesting papers afterwards, and actually written very in the time when it was almost impossible to question some foundations of this kind. He pointed out that actually some of the discoveries and some of the main points of relativity and formulas they were obtained by Lorentz not from the physical, really purely physical points of view, but they were obtained because of inability to resolve mathematical issues. Okay, so and some difficulties related also to this situation that such thing as metric become dependent on many coordinates, and there are some interesting works of Professor Santilli which take this deeper. So what I want to say here is that this is one of the lines of motivation where new kind of mathematics and mathematical structures need to be developed. Okay. another motivation, which actually a little bit closer to what I feel a little bit closer myself to, is that there are many processes in nature which are irreversible in the direct sense of this word, even because many processes connected to for example energy creation or some other such processes, they're clearly often irreversible, and when particles collide and new particles are born and so on, so there are many processes which are irreversible, and in mathematics, in this irreversibility of the processes often modeled and started using either non-invertible dynamics or stochastic processes. That is actually one of the way one can try to get to the situation of irreversibility of the system with respect to time, with respect to some other variables, and so on. And this is what is usually done. And for example, if you have a dynamics which can be some development in continuous time, or maybe it can be some iterations in the discrete time, and you have a map which easiest example of this would be a map which has several pre-images. And if you would like to go backwards in time, and you would like to iterate backwards, you don't know which pre-image you should take. So immediate. This is the simplest situation when you cannot really write inverse of the map. You have actually several possibilities for inverse. And interesting, for example, the fractals, which are so often referred to by physics and by engineers as something very interesting appearing in the real systems with non-immutability. They appear often as attractors of the inverse iterations of the non-inversible map. So if you take a map and take this inverse branches, you will get several maps, and then you start iterating them more. Then you will get many iterations in different order of these maps, and then if you take limits, then you would often get an attractor set, and that attractor set often has this fractal structure. So, for example, such sets as most known fractals can be obtained in this way. And the more complicated and the more complicated, interesting structures appear when you have iterations which are taken with certain probabilities. Then you come to the Markov processes and stochastic processes. So what I say is that these non-invertible processes are studied by various methods. But of course, for physics, for developing physics, one would like to combine this study of non-invertible processes with classical equations of physics, differential equations, and then arise various algebraic issues immediately, because as you know, for differential equations. This is very basic thing. It is evolution semigroup or evolution group, and if A is say linear operator, and you take this exponential, it is a exponential series computed on this. Then this becomes a solution of the ordinary differential equation, and you could, of course, this exponential functions comes also in solutions of more complicated equations, and this is how you describe the dynamics. You use this kind of quantities to describe the dynamics of physical systems, solutions of evolution equations, differential equations. But there are problems arising if you have. This, of course, if you look at this, if you put minus here, e in power minus at, this would be inverse to this. It's just if you take t and to minus t, it will be inverse of this, and times this, you will get identity operator, as one says. But if you have nonlinear dynamics with nonlinear transformations, and they try to write up the differential equations, then immediately one gets technical mathematical problems, but with using this kind of functions, or this functions, or this functions. Moreover, if you have, for example, two coupled systems described by say operator linear or possibly nonlinear A and B, and you try to compare this with this, then again you immediately get problem, because maybe this A and B do not commute, and if they do not commute with each other, as in many quantum systems, this appear and so on. But in any system where you have two paths which do not commute, then you cannot say that this is equal to this. And this actually one of the starting points for Lie groups and Lie theory. It's how to write up this kind of formulas connecting this with this kind of products. Yeah. And so in general, for non-invertible systems, it's not clear that it is the exponential function which play important role. So sometimes physicists from mathematical point of view try to stick in some functions or formulas which are given in the books and feed them and see whether data or computation of these formulas give you correct results with physical experiment. But if these formulas are based on this function and you have very highly nonlinear systems, you have to be very careful, because maybe these functions have nothing to do with the solution of those differential equations which you have. So there are several mathematical things one has to be aware here. And so Professor Santilli have examined many of these kind of questions, and already in end of 60s, actually, and in 70s, he pointed out that physics needs another unit element, because unit element, unit operator, this is a basic element which has certain invariant properties and which is very important for the whole theory. And then he faced the following problem, which is actually a problem which we study in and actually especially mathematicians get it built in our education, sometimes in some countries even from gymnasium level. So you see, if you have an algebra, you have an algebra of observables or whatever you need to use for a physical model. And it has no unit element. Then there is a standard procedure for joining unit element. Namely, you take elements of this algebra, you define some outside unit element, and you add times number and add it like this. And this is f. It can be complex numbers, real numbers, or any number field over which this algebra is defined. And and then you define product just by using distributivity law, and then it's fine. Then you get a new algebra with this product and with the unit, and you can work with this algebra. And usually geometrically this is connected. So, for example, if this with for example compactification of the space, if you consider algebra of functions, this would be often examples connected to adhering to corresponds to compactifying your space topologically. But there is a very basic problem, that if you want to have two units, so if you would have already a unit in an algebra, and you would like to introduce another unit which would depend, for example, on some parameters, like in Professor Santilli's work, and this something motivated by the physical considerations, then there is a problem to be resolved. Namely, if you write one unit and you write this, and then you write this, and then this must be equal to the other unit. I mean, this is unit. So when you multiply it, you have to you get back this, and so you can. It seems like that it's not possible to have two units in an algebra. So, but Professor Santilli said that we need to have it. So physics says that we need to have more units. So what is the problem? How to resolve it? And it was quite interesting that so early as end of 60s and 70s, he made the steps that and actually he did very true this in true mathematical spirit. He asked himself and he answered a series of correctly posed questions. Okay, so this means that we mathematicians, we usually ask questions ourselves and we solve them. And then the main point is to make correctly posed questions, okay, for us. So he said, what is mathematical reason for this problem? Okay, this is how I see what this point. And he said, he answered then. I assume this is how he was thinking. So he answered then that both the first unit and the second unit are units with the same product. So you have one product in the algebra, and you cannot have two units because of that simple computation if it is with respect to this one product, because that computation is valid, isn't it? And then he asked, okay, but we need to have two units or more units. So how to make this headache causing computation fail then? Okay, so what we should do so that this computation is not valid anymore, and so we don't have this headache anymore and can introduce these units depending on parameters and so on. Well, he said, since having this unit with respect to the same product is a problem causing this headache, then we simply need to introduce another product, and given a new unit element. So if you would like to introduce certain unit element depending on certain ways of some parameters, or maybe having some other properties, what we then should do? Well, introduce another product, and then the problem should disappear, because there is no anymore that uniqueness of the unit computation. And indeed, so if you have try to introduce the new unit here, either unit or as it's called, then you can define an element. If of course you can invert it, so you can write a new element T1 over this, or maybe this inverse. Yeah? And then you ask how to define this product. So you define this new product in this way, and that is really, I think, was crucial step, because most of mathematicians, they would add unit in this additive way, a plus lambda 1. Yeah, but modifying a product in order to add a unit, this is still quite fresh in mathematics. And considered to be an very interesting idea, especially in connection to this non-invertible systems and non-invertible dynamics. So this is a new product, and you see the problem disappear, because if you just formally write the first unit equals the same computation equal to, and then you write this first unit with this new product with the other unit. Oh, I forgot the hat here, but the other unit. This unit, and then you would write by definition of the product in this way, and then you would cancel this, and you would get the first one. So there is no any more contradiction. Okay. So basically, this is very ingenious solution, and to introduce a new product, and it is very much in line with such things which happen, for example, in connection to quantization, because there also you introduce different products depending on certain parameters. Of course, it is a question if you have, for example, star products, and introduce a deformation quantization with the star product. Can you express the star product by trying to choose this kind this kind of element? And it's very interesting mathematical issues and interesting problems connecting to this. And so this is very good, interesting way. And you see, when you changed, now you can do this change you can do this change. Let's see, maybe something happened with. No, sorry. Yes, when you do this change, then actually you can do this on the numbers. And so when you do this on the numbers, in number fields, it's okay. You can do this, and then you get this kind of either real numbers, either fields of numbers, and you can develop the whole number theory connected to how you multiply the numbers with the new products, and then another step which was taken by Professor Santilli is to go further and to introduce also introduce also possibilities of units from the left and from the right, and introduce two multiplications basically from the left and from the right, and which also correspond to ordering of the elements, and then one comes to this exciting area of general mathematics, which also closely connected to formulations using in another language bimodals and interesting is that this happens in the work of Professor Santilli and several other works of some of you much earlier than bimodals were used in connection, for example, to quantum groups, which is quite fashionable area now. But I should say that many of these deformations of the algebras they can be like quantum groups, so they can be viewed using this kind of modifications of the products. And you see, it's already this is work in 1967 in the Italian journal Nuovo Cimento, and I don't know if I pronounce in a very Italian way, but that's and many of you know this work. It's by Professor Santilli, and it is called embedding of Lie algebras in non-associative structures. Okay, and it was quite early, even from a mathematical point of view, to deform the brackets in this way. You see, it's commutative bracket, but it is deformed by two parameters, and then of course this is a special case of if you have such a product, you could put this parameter in between here, this parameter in between, and you see it's a difference between two such modified products in this sense. So it is just very early special case of this more general structures of which developed by Professor Santilli later. And now and of course when you modify these brackets in such a way with the parameters deform the brackets, then you maybe some of the axioms of Lie algebras might not be valid anymore, and this is what you observe in this Q. For example, there are these Q deformations of Virasoro algebra, of other algebras, and maybe you have some deformations of the Jacobi identity and basic identities, and it's interesting that so early as 1967 and this is probably because Professor Santilli had interesting line of motivation coming into this. Okay, so it was really an attempt to look at the fundamentals rather than in a very specific model of something and then modifying some variables and so on. He looked at really fundamental issues at that time. And you see, when you modify this bracket, and of course nowadays it's developed even for more general brackets. When you have t, you put t here and some other element here, so you have two units, and they might be, for example, in duality to each other. Then you can have various multiplication from left and right, but I wrote it still in this very early form. It's not trivial because you have now this evolution equation, or this you have derivative, and then you write instead of commutative bracket, you write this deformed bracket, and immediately arises issue whether exponentials become relevant and in which way when you try to resolve this kind of system of differential equations. Yeah? provided, and this becomes even more serious issue when you have brackets where you have put in some units which are nonlinear in local coordinates and so on and so forth. Then one has to think very carefully what you mean by writing up such a formula, and whether this and what you mean by this product, and whether such a formula would become a solution of this, and even what you mean by such a derivative, actually. Many of these issues have been, to a certain extent, quite successfully resolved in Professor Santilli and some of yours works, but still there are many issues here to answer from a mathematical point of view. You know, so it's not. Here there is one of the interesting thing for mathematicians to just issues connected to convergence of this. Is connected to how to interpret this formula so that this formula gives a solution, and the issues of looking at the if this variable t would be interpreted as time, but if you would have time, for example, discrete in some situations, then you maybe would not wish even to have some derivative here. You would maybe wish to have some difference operator of a certain scale. And that is something in numerical analysis now entertain themselves quite happily to discretize the time scale in various ways, and then writing up the equations and see whether one can find solutions or build up numerical schemes to this. Yes. So and you see this is more general. Brackets, which were also introduced in 78, so it's before quantum groups, and really where you put left and basically left-right units, and you define much more complicated brackets. And these elements, interesting that in what Professor Santilli suggested, these elements don't need actually to be members of the original algebra. They can be some external element, depending on certain parameters, and as soon as you can build up this, so basically mathematically, as soon as you can build up such a combination and make a sense of it, so that you can do this minus this, and inside the algebra and do further computations and compose them and so on. So then you can bring in a new elements here, depending which originally didn't belong to the algebra, and so there are the first kind and second kind algebra, so Santilli algebras and yes. So it's a different situation whether you have R and S already belonging to the algebra where A and B belonged, or you bring in a new element, but so that you still can do all computations with these quantities, and there's nothing wrong with this mathematically. Actually, it is quite exciting mathematical theory which comes out of this. And there are many applications of this. Which, for example, here's one of the works in Hadronic Journal in 1978 on a possibly admissible covering of Galilei's relativity in Newtonian mechanics for non-conservative and Galilei form invariant systems by Professor Santilli. I highly recommend this publication if you want to see the connections to relativity and Newtonian mechanics for non-conservative systems. And also actually Professor Santilli looked at the situation with Lie algebras and Jordan algebras, and he also provided discussion about symmetric and antisymmetric lifting of symmetric and antisymmetric brackets and then also there are various issues connected to Lie algebras, because the commutator is a standard. If you have associative algebra, associative product, then the commutator always a Lie product. So if you take commutator of AB minus BA, it will always satisfy Lie axioms. It's Q-symmetric and satisfies the Jacobi identity. And but if you change your associativity or this multiplication, and also define a brackets which of the form where you have two units, or maybe even more complicated, this left and right multiplication with left and right units. And you define such brackets generalizing commutator like A T B minus B S A, yeah, or something like this. Then suddenly the axioms even not true, not anymore Lie axioms are true. Maybe if you have the same unit element, is still you get into Lie admissible situation. But if you have two unit elements, then you get much more complicated algebraic structures. In any case, in Lie theory, there are important theorems. For example, Poincaré-Bergolf-Witt theorem, which describes any element as a linear combination of the ordered monomials in generators. And generators, they have physical meaning, clear physical meaning. So generators, they're generators of this evolution groups or semi-groups, so there's this separated a in the exponential e in power a t, yeah. And so if you take ordered products of powers of the generators and you take linear combinations of them, you get any element in Lie algebra, and this representation is unique. And this is a meaning. This is a formulation without formulation of the Poincaré-Bergolf-Witt theorem. For algebraists, this kind of theorems even possible to prove for not only Lie algebras but also for many other algebras given by commutation relations, where you can do this reordering uniquely. So if you can do reordering and derive to a certain normal form, which is in physics also there is this canonical or normal form for products in quantum mechanics and so on. So this is exactly the same thing. If you can do this, and there are certain criteria for this, something called diamond lemma in ring theory, then you can prove this kind of Poincaré-Bergolf-Witt theorems for various kinds of associative algebras, and even for some non-associative algebras. And here, of course, with the modification of the brackets arises the same question. If you want to modify Lie algebras, you want to modify Lie groups, you want to modify the whole build up differential geometry, lift up to this either theory and also to mathematic structures. Then you need to prove this kind of theorems, and actually Professor Santilli have made this kind of liftings for those brackets he defined, and also there were several other people involved, and many references and several books have been written in connection to this mathematical foundations and how to lift this basic and important theorems of Lie theory to this more general structures. Okay? So that's another interesting thing, and this finally, there are these issues about duality, because if you have I wrote again this in a very, very primitive way, but you can imagine that one could look at this product from the left, right, and so on, and have, important is that you have two units, okay, two elements representing these units, maybe depending on some parameters and so on. And these two units, they participate in the redefinition of the brackets and the structures and basic fundamentals of the theory. And these units, they allow for you to consider dependence on the basic quantities on the parameters. And in the beginning we've seen that there is a need, and some lectures that to look at the speeds of light, which are depending on some local variables. But it can be some other important quantities which you want to have dependent on some of these variables, and at the same time having some invariance properties with respect to some actions of some symmetries and groups and so on. And such if you have two units, then they might be in some kind of duality. And of course, this it can be this dagger which you use from physics, but it don't need to be in general structures and brackets like this. It don't need to be such a dagger. It can be some inverse or some other operation of which would satisfy these duality properties with respect to the products that you can. You can take this operation on the brackets and so on, and then you can use switch when you compute. You switch according to this rules, and then you would get some consistent algebraic structure. This is something also have been considered in Professor Santillis and others' works in connection to isotopic liftings and genomathematics liftings of Lie theory. Here again some applications, some work of Professor Santilli which connects to this kind of things to experimental work, and it's from 1978. But many of this it says the need of subjecting to an experimental verification, the validity with Hadronov and special relativity and power exclusion principles. And as I understand, some of the experiments have been now conducted, and they confirm that some points made by Professor Santilli at that early time, when there was no such equipment and this possibilities to do these experiments, are now maybe confirming the hypothesis that this kind of from a mathematical point of view, this kind of structures really related to experimental data and experimental the real physical situation. And here and you see it's so that it is so that maybe I'll show you about the numbers that what was introduced also by Professor Santilli this, and I mentioned this Gina numbers and Gina fields. So when you modify these products, but for number fields, and you even can introduce products and units from the left and from the right, then you get new fields of numbers. And Professor Santilli noticed that if you look at these new structures of Lie theory, and you want to introduce these units, depending maybe on some parameters, and you want to study further this kind of structures and really study connection to application and applications in physics in some experimental connection, you need really to go further, and you have to modify the basic concepts of numbers. Okay, so you have to introduce new numbers, new number systems in this way, in such a way, so that it suits the whole framework. And mathematically, I can very easily imagine that this is really needed, because if you because if you introduce a new product with new units, new elements, and these elements for you are so important, then they have to come in, for example, into formulas for representations of these algebras. So representations of the corresponding algebras, they usually have physical meaning, because as you know, maybe of course you know better than me that if you look at Lie algebras and you look at some eigenvalues of some Casimir operators, this would have a meaning of an energy or some other physical quantity. So, but now if you modify the Lie brackets, introducing very important for you this new units, and moreover modify the products using two products, from the left and from the right, so you have ordering from the left and the right, then immediately you can ask how you can get this energy levels from this computation, like for hydrogen atoms and so on, what you get there in eigenvalues. or and how you get representations, operator matrices representing this thing, it is really a new interesting step to say in this situation that the computations with usual numbers do not fit. You cannot, if you compute the same thing with usual numbers, you get the same thing as you started with. Yes. So you need to modify the numbers in your matrices, basically. So you need to modify the numbers in such a way that these basic quantities, these units, which you try to introduce, come into definition of these numbers. Then you could try to retrace the whole thing and build up from the scratch the representation theory for these structures, and try to see whether you can use these new numbers and develop representations of these algebraic structures and use them and give for in the same way as representations for algebras with usual numbers are used for physics, classically with like for hydrogen atom and Heisenberg relations, and this. So basically, this is very interesting idea to introduce these new numbers and then try to use them to recalculate and to obtain the development, the representation theory for these algebraic structures, these new algebraic structures with such modified products and modified units. And actually, this is still an quite interesting open direction for investigation in this general mathematics and isomathematics and in connection to physical experiments, and because this would give while physical experiments are developed supporting these ideas, this representation theoretical aspects which would be built and representation theory which for these structures built on this these numbers, these new number systems. That would exactly give that interesting connection and basis from the computational basis for this experiment. So I think the idea, the statement that one needs to use the such new number systems for this mathematical description and computations connected to Santilli's Lie extensions of Lie theory. This is fundamental, and I think it is a very correct way of doing things. So this is next step. So one has to really. So I just think about the exciting possibilities of developing the whole machinery of representation theory with decomposition theorems, with the reducibility of representations, with various questions there, but based for these structures but based, of course, on this Gina numbers and this kind of new number system. That is, I think, mathematically very interesting and new point of view, and very interesting for mathematicians. And I'm sure as you understand from my reasoning, that would be even very interesting for physicists working and looking carefully in this kind of models and new physical models based on this kind of structures. Yes. So I think. There are a lot of things for us mathematicians to do, basically here, and many problems which you pose, putting them in a more exact mathematical framework, and then resolving some of these issues using these generalizations of numbers and for this generalized and extensions of Lie theory. I think that's interesting direction both for physics and mathematics. And I would like to complete this by showing you that there are many works by Professor Santilli, and maybe for you who are interested in relativity, There is a book from '92 already, but there are also more new publications as well. So I think this is quite interesting for you who would like to look more into how this kind of structures are related to Galileo's and Einstein's relativities, for example. But there are of course more recent publications, and this I think I complete my presentation. Thank you very much for your attention.
Thank you, Professor Silvestrov. You are a mathematician.
I'm a mathematician. Yes. I don't hide it. I don't hide it.
Yes, and you see from the broader, the very, very broad. We physicists, we look at the little corner. Is it operating? Question, please.
Thank you for your very interesting lecture. I've not been aware of Dr. Santilli's work, but I'm honored that you gave the presentation. I have two short questions. First question was your large variable c is equaling to the speed of light over the index of refraction. So I'm going to ask you a very naive question. There's a class of materials which has come up with negative index of refraction. Okay, this is actually metamaterials that people would work with. They've been using that in things like for cloaking and invisibility. So the question had to do, which is, if you were working or tweaking with an index of refraction in that situation, given your new development, would that be consistent in explaining that sort of thing with respect to the theory to say, with respect to the wave function and the derivative of the wave function? That's my first question. My second question has to do with you talked about the Lie admissible deformations of the Heisenberg equation of motion. And I wrote this down very carefully. The R is equal to S star. And the question had to do, which is that your inverse of S and also to the inverse of R was related toward what you might call the left and right multiplicative type of invariance. So what I'm asking you is that what would the R equal to S, what would that give you in terms of additional information in the Heisenberg equations of motion? What would that give you in terms of new information that has not been provided before?
Well, that is a physical question. However, the information you will see it in my lecture.
Well,
mathematical question. This is a purely physical question.
Yeah,
even the first one is mostly physical.
Yeah, but Professor,
you have to sit and study at least at least 3,000 pages of. Yes, you have to first study then. In a few seconds, it's very difficult to answer.
Yeah.
But Professor Silvestrov, I can answer partially. Incidentally, the workshop in Nepal was on Lie admissible algebras, namely what you see the product that he has introduced. Those are Lie admissible. This conference in the particular case of Lie isotopy. So it's a major distinction which I have to do. And your answer should be first, if I may have a suggestion. Otherwise it becomes so complicated, the answer, that we'll lose each other in communicating. Should first be answered under the Lie isotopy case. Namely, you should ask the question in the particular case when R and S are the same and they are an invertible operator T. In this case, you verify the Lie axioms, and so you conserve all the beauty of Lie theory. That's why it's called Lie isotopy. And then the answer to your question is unique and unambiguous, and you gain convergence. The physical consequence, you eliminate infinities that nobody wants anymore, and no serious physicist wants anymore. You eliminate it because the series will converge very, very fastly under the condition that the operator R equal to S equal to T is in absolute value smaller than 1. Incidentally, all models that we have verified so far with experiments confirm this fact that the T, absolute value of T modulus, is indeed smaller than 1. So in these studies, infinities are totally absent. Professor Silvestrov, perhaps you can answer the first question, very important question. Thank you for, yes.
Additional elaborations of that in terms of Lie admissible representation, but I'll wait for after.
That you have to study the bimodule. You have to. The structure is a different. We can discuss it. But, I can give you a few papers in which first you have to study the structure and then. But thanks for your interest. Thank you, of course. Sorry, question please. I'm sure there are, yes?
In theory of Lie groups, Lie algebras are identified with the tangent space to a group manifold. If you added to Lie algebra some points, unit elements, for example, so what can you say about the modification of Lie group? Because you modified the tangent space. Yes. To a manifold.
Yes, that's one of the you see this one of the mathematical issues connected to what let me take this equipment. Connected to this because connection between Lie groups and algebras, it comes through Campbell-Baker Hausdorff-Dynkin formula, but of course writing up this kind of formula is a difficult issue when you have more complicated things here. Okay, even it is not clear whether exponential is anymore a most relevant function, or how you define it as rather exponential, analog of an exponential for this deformed brackets and for this kind of evolution equations, because you need to find the meaning of the exponential and meaning of putting in these variables into that new type of exponential, and there is a suggestion of how to do this in Professor Santilli's works, and in terms of this new structures, in terms of putting in these new multiplications and putting these heads and putting in this. There are books by Tsagas and Sorlas where they consider manifolds, differential manifolds, and these issues of lifting notion of differential manifolds and tangents and so on. And actually, I have this book lying in my hotel room just now. But you're absolutely right that when you modify the brackets and the multiplications, to write up explicitly all formulas to the level as it is done in Lie theory and recovering the generators of one parametric subgroups through taking derivatives and so on. This requires modification of the whole differential calculus to this kind, and there are a few interesting mathematical questions to answer there. But Professor Santilli has several very interesting works where he takes up these questions to certain very quite good level. So he writes up and explains things. But I think the idea of using this new number systems in this connection would be fundamentally interesting. So I think that would be the way to make it so explicit as it is done for Lie groups and the algebras. Yes.
Maybe I can complement again by long experience. Your question is fantastic, magnificent question, opens a new horizon of thinking. However, by long experience, this is the same case as the preceding question. My recommendation, by long experience, first work out the simpler case in which the Lie axioms are preserved exactly. Namely, when R and S are equal, then it's easy to verify that, and then you do the isotopy of the enveloping algebra, it's unique. Once you give the iso unit, it's unique. The enveloping of the Lie algebra, Lie first, second, and third theorem, the isotopy of the Lie groups, and so on. Then you answer uniquely and unambiguously to your question. But be careful that you have to use the word, the tangent space. It makes no sense in this theory. No sense. You have to redefine everything. Think in a different way. If the idea of elaborating the Lie theory by using isonumber is total nonsense. No, you use conventional mathematics to elaborate Lie theory. It's exactly the same thing. if you work at this higher level and you use conventional mathematics such as tangent space, it totally has no sense whatsoever. None. You cannot even define. You have to lift the entire notion of what the space is, because once you lift the number, the totality of the mathematics is lifted. But if you do it, it's very easy to do it at the isotopic level, and this is unique. At the more general level, which is your question, then what we are trying now is a bimodular theory in which the right and left modular structurally different. So we try to redefine everything on the right hand side, and then a complementary formulation on the left. But we have lost the axioms. So you see, this is when you go at that level, when R and S are different, it is a very complex mathematical problem. Yes.
But even at the isotope level, the physical interpretation, one of the physical interpretations is that you don't really lose the manifold, it actually becomes real. For example, you were talking about elasticity in your talk, but in general elasticity, one is actually talking about a real physical elastic medium, which is not a surface. Isotopes allow you to actually talk about a thick surface as opposed to a surface that has no thickness, for example.
It's a different way, even physically. You will see in my lecture the physical, some of the physical implications. Yes, please.
Short comment about this idea of forward motion and backward motion. I know very well and appreciate very much the theory of Santilli because it was a big contribution to the science in this direction. And what I can say about these kinds of motions, they introduce the idea of multi-times. Time in the forward direction, time in the backward motion, and these are connected with the theory of backward diffusion and forward diffusion. And if you look at these kind of problems, you attend stochastic processes which are differentiable processes, means similar to holomorphic functions. So they have derivatives, usual derivatives, and you can transfer the problem of diffusion into problem of stochastic aspect, volumetric dependence. Volumetric here means T1 multiplied by T2 multiplied by T3, depends how many times you need. Thank you.
Professor Udristis. Other question, please. Criticism, please. We are here to get criticism so that when we go home we can solve problems.
When you write this exponential, then you usually create a multivalued function, like e to the I phi. If you go phi, it's the same as phi plus 2 pi. So there must be also some multivaluedness in this reconstruction that you have. And therefore you have sheet structure.
This is a very deep question. Thank you, Michele, Professor Gilbert. We have three levels of new numbers, all verifying the axiom of a number. So the first is iso numbers, in which the unit is Hermitian and positive definite. And then we have a second level and verifies when you modify the product, then you verify the axioms. Incidentally, the old unit is no longer the unit, becomes an element of the field, it's no longer the unit. Under the new multiplication, only the new unit is unique. Then you have the unit when the unit is non-Hermitian, but invertible. That is what Professor Silvestrov has presented. Your question is very, very deep, because it's related to multivaluedness. But that has requested the assumption that the unit itself is multivalued. And you introduce a product that is, so 2 multiplied by 3 becomes virtually 10 to the results can be 10 to the 40 elements ordered. And your question is deeply, deeply connected to what the research is going on the deciphering the DNA code. Because you cannot decipher the DNA code with the number 1, 2, 3, 4, the unit 1, it's 4,000 years old. But the multivaluedness is crucial in However, we have to separate the multivaleness, for instance, in certain cases when we started light propagating in a medium. If we put multivalence, then we are lost. Only in certain cases.
So you can make advertising for my 3 o'clock lecture on multivalent fields.
Yes, but be careful, we will reinterpret in this formalism. We'll give you the invariance. We'll give you beautiful invariance. Other question, please?
It's not a question because I'm learning here. So you were talking more of Zeno, and he has just now explained ISO. What will be the hyper mathematics, or what you are mathematics? What will be the hyper mathematics in this respect?
That's what we said, multivalued. The unit is an ordered set of value, can be arbitrary, provided it is ordered, each one invertible, yes.
It's even more complicated.
They're much more complicated than this. Yes. And all of those levels submit an ISO dual map for an antimatter, which we'll see tomorrow. Other question, please? Michele, Professor Sacerdotti, come on. I know that your brain is ticking. Okay. Any other question? Yes, please. Criticism in particular, please, because still there are so many problems to solve. Thank you.
I would like only to comment question by Professor Katanaev about Lie algebra. It seems that there is situation is rather similar to superfield formalism. And of course, how it is proceeding superfield formalism. In fact, there is analog of Lie algebra, graded Lie algebras. So I think it may be applied here.
May I comment on this? Professor Sertile left, so I have no any more backup from his side. On that point about graded Lie algebras, I can comment. Well, yes, of course. So there are super algebras, and they are not Lie algebras, and then there are more colored Lie algebras also. So which are grading generalization of Lie super algebras to the grading of arbitrary abelian group, not only a group of two elements, and they are generalizations of Lie algebras. Many, probably all, but definitely many of them can be put in this framework of such brackets. So this super algebras and colored Lie algebras, they can be super Lie algebras and colored Lie algebras. They can be viewed from point of view of such more generally deformed brackets. And also there are many of these Q deformations of Lie algebras. And actually, interesting thing is that Lie super algebras and colored Lie algebras, they often appear as the limits of the Q deformed Lie algebras when Q goes, these parameters Q or maybe several parameters go to mass 1 or minus 1. And this you can see in the examples when you compute with the Q deformations of Lie algebras. But all of these kind of structures where you deform the bracket by various parameters, they can be in one or another way put into this framework of deformed brackets defined by Professor Gentile. Of course, maybe not. This is one of the examples. But when you put here arbitrary elements T and S, then you can adjust this T and S to get very complicated deformation. And when you take limits, you recover Lie super algebras, Lie algebras like recovering commutator or anti-commutator. So your question about generalizations of Lie algebras to graded situation, I would say that these graded situations, they are special cases appearing in the limit transitions from such deformed brackets. That is my point of view, and that is what I see in the examples when I computed with this colored Lie algebras. And I actually wrote several papers about this colored Lie algebras. And, so that's,
I would like to make one. I see there are several colleagues here interested in geometry, including my dear friend Professor Cord. If you use a single Hermitian positive unit, you can lift the very, very structure of the geometry and in an axiom-preserving way. For instance, you will see in my lecture for Minkowski, Iso-Minkowski, the metric becomes arbitrary, but the axiom remains locally isomorphous. Was proven by Professor Sagas and other this notion of isomanifold. In gravitation, there's lots of things to do by preserving the axiom of Riemann and the formalism, but enlarging the functional dependence of the metric, because while excellent for the historical part, now it's become excessively restricted for interior problems and so on. So, but again, you have to lift each and every aspect, to start from numbers. Everything has to be lifted. The differential calculus, functional analysis, everything. If you do it, it is rewarding, because we honor in this way the originator. Riemann remains, at the abstract level, remains Riemann. Only we introduce broader realization.